To use the formulas associated with linear regression, you have to first take your data on x and y and create so-called summary statistics, like the sum of x times y or the average y, because you put those in the formulas. This scenario with the building supply company and the insulation rolls, the key to this scenario is that that work has already been done for you, the summary statistics. You just have to know where to find them in the paragraph. Let's look. The manager of a building supply center suspects that the monthly sale of rolled insulation for installation in attics depends on the average air temperature during the month. Oh, okay, so here we have a classic hypothesis for linear regression where the monthly sale of rolled insulation depends. That means it would be the dependent variable, or y, right? And it depends on what? The average air temperature. Okay, so that would make air temperature x. All right, now, moving on. The manager has a spreadsheet with, now see, here comes some data. 42 months of past data, actually, all right, on this subject, in which the overall average monthly air temperature was 49 degrees. We were saying that x was the air temperature, and I just found x bar, or the average x. That was just described to me. All right, what else is described to me here? And the overall average sales for rolled insulation is 428 rolls a month. We just said that the sales are what we hypothesized as y, so y bar is the average sales. 428 is what we're told. Okay, what else? On that spreadsheet, the manager has created a column in which each month's average air temperature, we were saying that that was x, is multiplied by each month's sales. Okay, we were saying this y, and then these 42 numbers are summed together, sigma, to create a very large number. 873,931. In another column in the spreadsheet, the manager has squared each month's average air temperature. Each month's average air temperature, the manager has squared it and then summed the 42 readings together, sigma for sum, and gotten another large number. Obtained the value of 105,080. Okay, now it says next month the average air temperature is expected to be 35 degrees Fahrenheit. Use linear regression to predict next month's sales, which is to say, here's the hypothesis again. Sales, we hypothesize, equals, okay, some number plus some other number times the air temperature that month. Air temp. We just need this number, and that, for convenience sake, was pre-printed on the note frame, right? Because A is known as the intercept of the regression line, B the slope, and this is right here, the formula for the slope, and there's the formula for the intercept all ready to go. Those formulas require the summary statistics that were just described to us, and now we're all set, because now all we need to do is fill in the formulas. So let me do that. Now we want to do that carefully. Let me think. All right, let's do B first. Actually, we have to do B, the slope, first, because you need to plug that into A. So I'll say B, the slope, equals the sum of x times y. That was the big number, 873,931, minus n. Now wait a minute, where's n? Oh, I forgot to jot down n as we were going through the scenario. N is the number of observations in the data set. That was that first thing that I underlined. Here n is 42, because it kept talking about 42 months, 42 months. So anyway, we want to say 42, now wait a minute, what's up here in the numerator? 42 times the average x, okay, that was 49, times the average y. Average y was 428. Okay, the numerator is all filled in now. Divided by the denominator. The denominator is the sum of the squared x's, and that was 105,080 right there, minus, again, n, 42, times the average x, which is 49, except careful, square it. All right, so I put that in my calculator. In the numerator, I got negative 6,893, and in the denominator, I got 4,238. So this formula, the result is, well, basically a negative 1.63. Okay, now, that's this part. Got it. Okay, now we also need the intercept. Now the intercept is easy to find because the intercept A, I'll just squeeze it in here. From the formula, the only thing that we need is the average y, okay, 428, minus b, minus the result here. So minus a negative 1.63, minus a negative is plus, it reverses it, 1.63 times the average x, which is 49. So this A, the intercept, I got 507.87. Basically, I'm going to round 508. 507.8 some odd, 508. Oh, okay, now fine, we filled out those two formula. It still said something about predicting next month with an average temperature of 35 degrees. Oh, we have to now put them together into the finished formula. Here's our hypothesis based on linear regression. We are thinking that sales, that's Y, can be estimated by 508, right, my A, 508 plus B, right, this is, except wait a minute, except B itself is negative, plus B, or minus 1.63 times, oh, the only thing that's missing here is X, right, X is the air temperature. Now, we're trying to solve the first part of the scenario, and we're still getting there. But what did it actually ask? It asked, next month, the average air temperature is expected to be 35 degrees, so what do you think that the sales of rolled insulation will be? Now we want to use, finally, the linear regression expression that we created by just substituting in that 35, y equals 508 minus 1.63 times 35, right? That's what we expect the air temperature to be. Or, like, 450.95, pretty much. Come on, it's got to be round numbers if you're proposing rolls of insulation. Pretty close to 451 rolls. So, all right, so based on linear regression and the fact that we expect next month the average air temperature is going to be 35, we're estimating that they're going to sell 451 rolls. Okay, good. Now, that's the first part of the scenario. Let's look at the next part. Next part. Next part, there's like more facts. The sum of the 42 months of air temperature readings is 2,058. Okay, air temperature readings is X. The sum of those 42 months, I'm adding them up. Oh, the sum of X equals, okay, and good to know, 2,058. And the total sales of rolled insulation over the same period is 17,976. Y, monthly sale, we're adding them all up. This is another summary statistic, 17,976. The sum of the squared monthly sales of rolled insulation is a very large number. Okay, the monthly sales of rolled insulation is Y. The squared monthly sales is Y squared. And sum up is sigma. That's how you describe that really large number. But I skipped one because it says total sales are, oh, no, I'm good. What percent of the variation in the sale of rolled insulation is explained by its linear relationship to the average air temperature during the past 42 months. Oh, well, you know, there was a formula that was put into the note frame just to be handy, so we're assuming that the answer to that question is going to have something to do with that formula. But wait a minute, what is that question asking? It says, what percent of the variation in the data is actually explained by that expression that we came up with in the first part, the 508 minus 1.63 times x. That is known as r squared, or the coefficient of determination. That is how you describe the coefficient of determination. R squared expresses the percent of variation in the actual past 42 months of data that is neatly explained by that one equation that we came up with. Oh, all right, well, we said, well, we don't have the formula for R squared. Right, but it's just the square of the formula that we do have. So let's fill out that formula that we do have. We just want to be neat and tidy. In the numerator, let me try, we need n, that's still 42, times the sum of x times y, that we were told originally. Okay, so that is that same 873,931. Okay, so we got that part of the formula. Minus the sum of x times the sum of y. That's why we were told those two things originally. Okay, so, minus 2,058 times 17,976. Okay, so we have that part, that's there. We have that part, that's there. That's the numerator. The denominator, all right, let's break it down. It is a big square root, but I'm not going to draw that yet, because first I want to fill in, see how there's like two halves here? This half, n 42 times the sum of the squared x's. We were supplied that is 105,080. That was from the original paragraph. Minus the sum of the x's, well, that's just that 2,058, except be careful, square it before you do the subtraction. Okay, the different style of brackets helps us keep track a little bit here. That's that part. This multiplied by, let's do this part. Okay, well, n is 42 times the sum of y squared. Oh, that's the big number, the 7,710,080. Okay, that's that minus the sum of y, 17976, except careful, square it. Okay, this, I need to remember, is all under a square root. There, at least I have all of the numbers in place now. All right, well, I start putting them in my calculator. In the numerator, this is what I get. 289,506, and careful, it's negative. So it's a negative 289,506. Divided by this, the first set of the first brackets here. I'll break it down. I get 177,996 times, in here, what I get is 686,784, and we have still, as of yet, to take the square root. When we do that, what my calculator is displaying is a negative 0.828 with some rounding. You know, phew, we filled out that formula, but we haven't answered the question. because that formula only gets us R, or rho, or the so-called correlation coefficient. We are in pursuit of R squared, the coefficient of determination, right, which is just that number. We're almost there, but we have to square it. So if you say negative 0.828, square it, you're going to get a positive number, 0.658, which can also be expressed, this is optional, as 65.8%, because we are answering the question that in that 42 months of past data that's on the manager spreadsheet, what percent of that variation is explained by the regression equation. And what we're saying is, well, it looks like a little less than 2/3, 65.8%. R squared is 0.658. All right, so that answers the second part of the scenario. You think, oh, what else do we have to do? Well, the third part of the scenario, it asks, what is the value of the correlation coefficient, or a measure of the linear relationship between the average air temperature and the sale of rolled insulation? What does this value suggest about the relationship between average air temperature and the sale of rolled insulation? The good news is we've already done the work to answer that question. Because in the second part, we were working on the coefficient of determination, R squared. So in order to calculate that, we calculated R, and that is the correlation coefficient. That's what the third part's asking for. So now this is easy. We say, well, it's a negative 0.828. All right, well, that answers the first query. The second query was this saying, what does this suggest about the relationship between the average air temperature and how much rolled insulation that they sell? How do you interpret a correlation coefficient? Well, correlation coefficient will range between 1 and -1. If it is close to -1, which this is, a negative 0.828, it is suggesting a strong negative correlation. If it's close to +1, it's suggesting a strong positive correlation. So what does that in turn suggest about like rolled insulation and air temperature? Well, strong negative correlation. That would mean when air temperature goes down, sales for insulation go up. They work in opposite directions. So I'm also adding and vice versa, because I don't want to write it out, but that implies that when air temperature goes up, the sales for rolled insulation is going to go down, which sort of makes sense. When it gets colder, they sell. When it gets colder and the temperature goes down, they sell more insulation, and thus the sales for rolled insulation goes up.